Perception faults are critical because they compromise localization and decision-making, yet they are often overlooked in autonomy pipelines. In vision-based LAM, such faults typically arise from visually deprived conditions, sensor damage, or dynamic scenes, which this video will mainly address. These faults lead to failures in both front-end and back-end modules. We propose a fault detection and isolation (FDI) framework for perception systems that predicts outputs under fault hypothesis using counterfactual reasoning and leverages control inputs to enhance detectability and isolability. The perception system generates reliability test signals from intermediate outputs such as feature counts and image quality metrics. The FDI module compares these signals with predicted distributions under different fault scenarios. To reduce false alarms, we maximize effective information, a causal information theoretic metric, by actively choosing control inputs that strengthen fault diagnosis while maintaining tracking performance. We evaluate our method in an asteroid exploration scenario where our spacecraft relies on vision-based navigation. 3 fault cases are considered critical: sensor faults, dynamic scenes, and visually deprived conditions. Each is studied in both mild and severe forms, depending on its impact on pose estimation accuracy. In the simulation, the FDI module is activated after 1 second. We compare the performance of passive FDI with a baseline threshold-based method, as well as with our active FDI approach. In severe cases, all methods successfully detect and isolate faults with similar effective information values. In mild cases, however, thresholding and passive probability-based FDI often fail. By contrast, our active FDI method, which exploits control inputs, increases the likelihood of encountering disambiguating fault patterns and achieves faster, more reliable isolation. Random control fails to maximize effective information and performs worse than our active approach. In summary, counterfactual reasoning combined with active control improves the detectability and isolability of perception faults. Our results demonstrate that the proposed active FDI method offers more robust and precise fault diagnosis, a crucial step toward achieving trustworthy autonomy.